Hi, my name is Patton. I go to the Colorado School of Mines. I'm going to be a junior next year, and I'm majoring in engineering physics with a minor in renewable energy. So, what I did this summer is I studied amorphous and nanocrystalline silicon, disordered semiconductors, and I guess the first things first, amorphous silicon is basically the bread and butter of photovoltaics. It's the first commercially produced PV modules. So I was just looking at that, and the only problem with amorphous silicon is that it degrades in sunlight. And then as compared to the crystalline silicon, which is the blue line, it degrades very little in sunlight. So that's one of the properties we're looking at, which is really exciting about the crystalline silicon. And another really exciting thing about nanocrystalline silicon is that it can actually absorb the photons below the band gap of amorphous. So that means it has potential for greater range of absorption and higher efficiency photovoltaic modules. So a little bit about what I did this summer is I took 3 different mixtures of silicon. I took about one that was mostly amorphous silicon, which I don't know if you can see this cartoon. It has very little crystals in it. Then I took one that was about 90% crystalline, which is this little cartoon here, and then one that was a mixed phase, which is about 50% amorphous and crystalline, which is this one right here. So the first test I did was Raman scattering, and what this shows is the crystalline fraction of each sample. And let's see, the red one is the mostly crystalline, so you can see it has the highest crystalline fraction. The blue one is the amorphous and it has the lowest crystalline fraction, and the black one is the mixed phase, which is about the middle, and the combination of the two, which is what we would expect from these samples of silicon. So the next thing I did was electron spin resonance, which I'll give you a little bit about electron spin resonance. It's 2 huge coils of wire that create a magnetic field, and what they do is measure the defects in the samples, and the defects really are created from the dangling bonds, which are mostly in the amorphous phase of the silicon. So what we looked at here, well, actually we know it's in the amorphous phase because pure crystalline silicon has little to no ESR signal. So what I was looking at is the differences in room temperature ESR, which is this graph here. I don't know if you can see this red line is the amorphous, and the black one is the 90% crystalline. And what's really interesting about this graph right here is that I've never really seen anything like this shape before in any literature that I've looked at. This little lip here, it can't really be fit to either a Gaussian or a Lorentzian derivative. So that's kind of interesting because you can't calculate spin densities of it. And basically spin densities is the concentration of dangling bonds in the material, which are defects, which are bad because electrons get stuck in the carriers and electricity doesn't flow as well through the photovoltaic modules. So we're trying to mitigate those defects right now. This graph right here I found from an earlier paper, and it was a similar measurement to mine, except it was done with about 50% nanocrystalline silicon, and it just shows that the 50% and 90% are actually quite similar in the room temperature measurements. The next thing I did was look at light-induced, and that's what this is. Light-induced ESR, I did it at about 40 Kelvin, so I used liquid helium, and what I did is I took a dark measurement, and then I shined an infrared laser on it, and then I took the difference. So the fact that there's the difference between the dark and the light means that the photons were absorbed, and it actually changed the material. So as you can see here, this is actually this is actually due to the holes in the material, and this is due to the electrons. And this is when the carriers get stuck in the band tail states. So what that means is that, going back to this graph, the amorphous degrades a lot in sunlight because it creates more defects in the material, which is bad. So what I was trying to do is reproduce this experiment right here, which is also light-induced, and it shows nanocrystalline, which is the top two, and amorphous silicon, which is the bottom two. And what I am trying to do is mitigate the effects of the light on the silicon. So what we determined from this is that because the amorphous degrades a lot in the sunlight, and the 90% crystalline also has a lot of defects because it has a lot of grains, and there's about one defect per grain on each of these crystallites. What we determined is that about the 50% mixture, which is this one, is probably about the best for photovoltaic modules because it's the best of both worlds. So the conclusions are that 50% is probably the best for PV, and also that the charge carriers are most likely getting stuck at the band states due to the ESR signals. And I guess that's about it.